Hi, we're going to cover orthogonal diagonalization and the quadratic forms. Definition: a real n by n matrix that is invertible is called orthogonal if the inverse of A is the transpose of A. Here's a theorem. Let A be a real symmetric matrix, then number 1. All eigenvalues of A are real. Notice that I'm highlighting real symmetric matrix. This is mainly what we're doing in this section. Just keep that in mind. Real symmetric matrix. Eigenvalues will be all real. Here's number 2 also highlighted. We're going to use it also in this section. Real eigenvectors of A that correspond to distinct eigenvalues are orthogonal. Just keep that in mind. I'm going to refer to it later on. Real eigenvectors of A that correspond to distinct eigenvalues are orthogonal. So they already come orthogonal. You don't have to make them or force them to be orthogonal. They're already orthogonal. Number 3. A is non-defective. Number 4. A has a complete set of orthonormal eigenvectors, which means non-defective also. A can be diagonalized with an orthogonal matrix S, such that S inverse AS is diagonal. Alright, now find a complete set of orthonormal eigenvectors of A. Notice A is 2, 2, 1, 2, 5, 2, 1, 2, 2 is a symmetric matrix. See, one of the benefits of the symmetric matrices is it's going to be non-defective, and as I mentioned in number 2, eigenvectors that comes from distinct eigenvalues will be already orthogonal. Let's move on. So we know how to find lambdas. We're gonna go for the determinant of A minus lambda I, and this is what we have. So we have two lambdas, as you could see. Lambda 1 equals 1 with multiplicity of 2, and we go back and put 2 in. A minus 2 times I V equals 0. We solve for it, and we get V1 plus 2V2 plus V3 equals 0. So it's only one line. We have two free variables, of course. With two free variables, V2 and V3, let's call V2 equals R and V3 equals S. With that in mind, we're going to have V1 by itself, which is minus 2R minus S. Taking R and S out as factors, we get the corresponding eigenvectors. We get minus 2, 1 and 0. We get minus 1, 0 and 1. So 2 eigenvectors for lambda 1. Next. So we have two linearly independent eigenvectors corresponding to the eigenvalue lambda 1 equals 1. x1 purely negative 1, 0, 1, doesn't matter which one is x1 and x2. x2 is negative 2, 0, negative 2, 1 and 0. Now we are still within the same lambda, so x1 and x2 is not an orthonormal set. You can test that if you do the dot product and so on. We can apply the Gram-Schmidt process to replace the set with an orthonormal set U1 and U2 as follows. Just want to write the steps down in case if you need to go back and find out the steps of doing that. We had that a while ago. We take V1 equals x1, we keep V1 as is from x1, and V2 we build the projection and we move on, then we do subtraction. So v2 becomes x2 minus the projection of x2 over v1. You have the steps, you could verify it. We end up with minus 1, 1, and minus 1. Now these two new vectors, which is minus 1, 0, 1, I'm using the same colors as you could see to refer to which one is which. Negative 1, negative 1 is an orthogonal set. Okay, we're done with lambda 1. Let's go to lambda 2. To obtain an orthonormal set, we divide each vector by its magnitude. Those are orthogonal. To find the orthonormal, you find the magnitudes and you divide by the length. For example, this one, negative 1, 0, 1. The magnitude will be negative 1 square plus 0 square plus 1 square under the square root. And that is 1 plus 0 plus 1 under the square root, which is square root of 2. So we're going to divide this everything by square root of 2. That's coming in the second step, as you could see. So negative 1 override 2, 0, 1 override 2. This will give you square root of 3. You divide by square root of 3, that's going to be the orthonormal. Okay, next. Lambda 2 was 7, so you go back and plug in 7 for lambda and you solve for the determinant, and we end up with one vector which is 1, 2, 1. The length or the magnitude of 1, 2, 1 will be 1 square, 2 square, and 1 square. That is under the square root of 6, under the square root, which is square root of 6. So this becomes a unit. Now let's summarize what we have. Now u3 is orthogonal to both u1 and u2, as stated by the theorem mentioned earlier. Lambda 1 gave me two vectors. We made them unit vectors, and we used the Gram-Schmidt to make them perpendicular to each other. Lambda 2 gave me one vector, which is right here. Now this will be already orthogonal to u1 and u2. We don't have to use the Gram-Schmidt right here one more time. One more time, the theorem in part 2 says vectors, eigenvectors coming from distinct eigenvalues are already orthogonal. This will be orthogonal because it's coming from a different lambda, from distinct lambdas. So a complete set of orthonormal eigenvectors for the matrix A is u1, u2, u3, and that is right here u3, and u2, u1 came from lambda 1 equals 1. So if we set S equals the column vectors, as you can see, this right here is u1, this is u2, and this is u3, then S is an orthogonal matrix satisfying S transpose AS equals S inverse AS, or in short we use the diagonal matrix of the lambdas 1, 1, 7. Alright, so it's clear. I mean, we used the Gram-Schmidt because we had two vectors within one lambda, so we had to use a Gram-Schmidt. In lambda 2 we did not have to, and now we have it. This is back to earlier section that we build S from the eigen vectors. Note, the advantage of a real symmetric matrix that we're dealing with is that for such a matrix, the eigenvectors from one eigenspace and the eigenvectors from a different eigenspace are already orthogonal. Quadratic form. Now, what is quadratic form? A with a size of n by n is a symmetric matrix. X is the column n vector in R to the n. We call X transpose AX the quadratic form. For example, If n equals 2, we have the following. So two variables. This is the matrix 2 by 2 times 2 by 1. So we have a system of two equations with two variables, x1 and x2. If this is x, the variable matrix, this would be the transpose. The first column will be the first row, and that's how we do that transpose. Alright? Next. Notice that a21 and a12 are the same. Since a is symmetric, I wrote these two numbers as identical. So I'm using a different color here to show that pay attention to these numbers. They have to be identical to be called symmetric. Now, multiplying this by this, we have this matrix 2 by 2. We're going to multiply this matrix by the new matrix, and we're going to end up with the following. Since a21, as mentioned right here, and we have symmetric matrix, A is symmetric matrix, these two are the same, because you could call a21 and a12 just A, for example, or a letter C. They are identical. We combine these two, and we have now this form. The first term is second degree, the last is a second degree, and the middle one is twice a12 x1 x2. It's called quadratic in x1 and x2. The question is whether it is possible to make a linear change of variables x equals sy, as we did earlier. Making the change of variables x equals sy in the quadratic form gives us the following. This is the left hand side, x transpose ax. We're going to replace x with sy both ways. So now we're going to take the transpose of sy. Remember, the transpose of AB becomes B transpose A transpose. It's kind of like switches here. Just pay attention, and those are properties we took a while ago. So, as mentioned, it's Y transpose S transpose AS Y. We choose S to be the eigen vectors as column vectors. W1, W2, all the way to Wn will be a complete set of orthonormal eigenvectors of A. Now, we used in the previous example to call them U1, U2. It's the same thing. Those are U1, U2, U3 up to Un. So we have S transpose AS will be the diagonal of the lambdas that we have. With the choice of S, that we take the column vectors of the eigen vectors. With the choice of S, the right hand side of this equation reduces to the following. So we have y variables, yn variables. That's the transpose of y right here. And instead of using the S transpose AS will end up the diagonal y1, y2 lambdas right here. Now let's multiply. When you multiply and you take your time, you're going to end up with lambda 1 y1 square, lambda 2 y2 square, all the way to yn lambda n square. We then reduce the quadratic form to a sum of squares. Earlier we had quadratic form. First term was second degree, as an example of n equals 2. The last term was also second degree, and the middle term was twice, kind of like twice AB, the way we talk about middle term. But this is now what? It's a sum of squares. When we choose S as the column vectors, right here is a complete set of orthonormal eigenvectors of A, we could do this right here and use the linear change x equals sy, and we end up with the sum of squares. This is called the principal axis theorem. A matrix A with an m by n, a real symmetric matrix, the quadratic form x transpose ax can be reduced to a sum of squares, as we saw earlier, by the change of variables x equals sy. S is an orthogonal matrix whose column vectors w1, w2 up to wn are any complete orthonormal set of eigenvectors of A. The transformed quadratic form is, this is just like a summary, as you could see, lambda 1 y1 square plus lambda 2 y2 square plus all the way to lambda n yn square, where lambda 1, lambda 2, lambda n up to lambda n are the eigenvalues of A corresponding to the orthonormal vectors w1 up to wn. The column vectors of the matrix S in the principal axis theorem are called the principal axis for the quadratic form x transpose ax. Example: by transforming to principal axis, reduce the quadratic form x transpose ax for A equals 2, 2, 1, 2, 5, 2, 1, 2, 2 to a sum of squares. Now, we did in the previous example, you remember when lambda 1 was 1 and lambda 2 was 7. For lambda 1 we found two vectors, and then we used the Gram-Schmidt to make it orthogonal. Then we did the unit vectors. That's these two right here. Lambda 2 was 7. We came up with 1, 2, 1, and then we changed it to a unit vector. So this is S, a complete set of orthonormal unit vectors, and the corresponding eigenvalues of A are 1, 1, 7. The change of variables x equals sy reduces the quadratic form to simply 1, that's lambda 1, y1 square plus 1, which is lambda 1 again because it's repeated lambda, y2 square plus the third lambda, which is 7, y3 square. It's a sum of squares. Now, this is a simple form compared to the quadratic form, expressed in the original variables, namely x transpose ax equals x1, x2, x3. See, for this one right here, it's a 3 by 3. When you do the quadratic form and you apply x transpose ax, you will get this right here. We prefer this one right here. It's called sum of squares instead of the quadratic form. And as you can see, the change of variables x equals sy reduces the quadratic form to a sum of squares. And that's enough for 7.5, or orthogonal and diagonalization and the quadratic form with the principal axis theorem. Thank you for watching. I hope that it was helpful. Hit the like button if you do like it, subscribe, comment below, and if you like this video, I'm making more soon Right after this one, I'm gonna go to chapter 8 and start working on 8.1 and 8.2. That's gonna be uploaded hopefully today. All right. Thank you very much. Until next time, peace. JaberTime.